Hey, what's up? What's up? It is Friday, October 6th. All right. So, you know what to do. Agenda. Let's get right into it. Let's go ahead and move that along. All right. Cool. So, just remember this. This is due next Thursday. So, next Thursday is the day that it is due. So, make sure that you guys get this in, get it turned in, make sure to ask the last minute, all of those kind of things. Get this fundraiser done because we have to turn it in on October 12th. All right, cool. So also I do want to say there is a quiz. Originally I was going to have it on Tuesday, but we're moving that quiz all the way to Thursday, October 12th as well. So we got the fundraiser October 12th. We also have the quiz October 12th. Let's go. These are the things that will be on there. So things about claim, evidence, reasoning, all the vocab that we've been going through, and the linking literacy. So we've had 2 linking literacies, especially the one we're about to do right now. Make sure you know all the things on there. Okay, cool. So I do also want to just say this. These are all things that we should already know. So if we look up top right here, we got motion, which is the change in an object's position with respect to time. We got interacting objects, right? That's right up over there. Those are objects that affect one another directly because they come into contact or they have what is known as a collision. We got down there, we got force is a push or pull, right? And then over there, we got Newton's third law, which is for every action force, there's a what? Hopefully you got equal and opposite reaction force. These are ones that we already know. Nothing new there. Okay. Cool. So now let's move on to this. We have been talking about acceleration. Oh, let me go back. We've been talking about acceleration. So make sure to get everything that's on this page. Yeah, all of them drawings down there. You need all of them, everything that's down here. So acceleration is a change in motion caused by unbalanced forces. We talked about this yesterday. Acting on an object, and this includes increasing speed, decreasing speed, and also changing direction. So if an object does any of these things, if it increases in speed, if it decreases in speed, or changes direction, then you have what is known as acceleration. So pause the screen if you need this note. If you still need to take it, Mr. Farr is moving forward. Okay, cool. So here's an easier one. Direction, a straight path that an object can move along. A straight path that an object move along, that is direction. Okay, boom. And again, pause the screen if you need it. There's not a lot to say here. Again, this is a very common term. So again, a straight path that an object can move along, because that is known as direction. Yes, it is note-taking time. Yee. Okay. Now, this one right here, net force, that is the sum of all the forces acting on an object. So if we added up all the forces that are acting on an object, we would call that net force. So now what I want you to do is take some time. I know it's a tiny bit blurry, but try and calculate the net force on each one of these. Now we did these already before. So again, pause your screen and try and calculate. After you've taken this note, calculate the net force on each one of these. Make sure to show your work. All right, so hopefully you got all those up. We're going to take a look at these answers real quick. Blat out. So let me see if you guys can. Oh, there you guys go. Boom. So get it a little bit out. These are the answers that you got. So we got number 1. We ended up with 4 newtons. Number 2, we ended up with 5 newtons. Number 3, we ended up with 0 newtons, or on, right? Number 4, we ended up with 6 newtons. Down here at number 5, we ended up with 4 newtons as well. And then number 6, if you look, I messed it up. I put the smaller number first. You always got to put the larger force first. So we ended up with 1 newton. So if you take a look at all of these, which one do you expect for no movement? Hopefully you said that it would be number 3, because we have 0 newtons or balanced force. So if in that case, if they're both pulling apart at the same force, we would expect 0 movement. Slowest movement, that would be 6, because it has the lowest amount of net force being applied. And then what we would say is the fastest one that we would expect to move is this one with 9 total newtons of net force. All right, so hopefully those are questions you could be able to answer, and hopefully this is what you got. If you had a quiz, how many answers did you get right? Now, if you didn't do any of them, then you got 0. That's bad. So make sure when Mr. Farr is like pause, do the work, that you actually pause and do the work, because you want to get the most you can out of these lessons. All right, cool. So let's move it along. Let's move it along. Let me put my clipboard down. We moving along. Wow, at least I think we're moving along. I'm not sure what we're doing. Okay, so this is actually the last note for today. So make sure to get this all down. We're going to talk about this, and then we're going to go. Yeah, actually, this is the last note for the day, and then we're going to go a little bit deeper into this. So Newton's second law, the acceleration of an object is directly proportional to the net force and inversely proportional to its mass. Okay, so a free body diagram, just so you guys know, free body diagram are diagrams that show the net forces acting on an object. And if we just go back, right, let's just go back real quick. Let's just go back. These here are all free body diagrams because they're showing the forces acting on an object. Now they're not showing all of them. Now in the lab, you actually drew those as well. So they're not showing all of them. But again, those would be what we would call free body diagrams. So let's just talk about that first. Now let's move on to the first part of Newton's second law. So the acceleration of an object is directly proportional. So if you look right here, is directly proportional to the net force. So if you look right here, as force increases, so does acceleration. So just like I have this bottle right here, right? So as I increase the force, boom, it moves fast. Boom. I know it's that. But as I decrease the force, so also when force goes down, acceleration goes down. Look, I decrease the force, then also its acceleration goes down. So that's what you see. So increase the force, boom, moves fast. If I decrease the force, then acceleration goes much further down. Okay. Now, on the total opposite end of that, and the last part of Newton's second law says inversely proportional to its mass. So inverse means like the opposite. So that means if mass goes up, acceleration goes down. So that's why you see this. If we had a Honda Civic and then we also had a diesel truck lined up right next to each other, and we applied the exact same amount of force to each one of them, which one do you think would accelerate faster? It would be the Honda Civic. And the reason being is because it has less mass. This is also the reason why when they design cars, they're like, we don't need as big of an engine in the Honda Civic as we need in a diesel, because we don't need to generate as much force to the wheels to get the car to move, because the car has a lot less mass, so we don't need as much force to get it to go fast. Now, I do want to say this as well. You have been on a freeway, I would presume, and you've driven next to a diesel going the same speed as you. Now, just because two objects are going the same speed does not mean that they're outputting the same amount of force. That's why that diesel's engine is so much bigger. It's putting out so much more force in order to get that truck, that diesel, to move at the same speed as the Honda Civic. Has a much smaller engine and is putting out a lot less force to get the object to move at the same rate of acceleration and speed, because of the fact that the diesel's mass is so far up that its acceleration is down. But then the Honda Civic, its mass is down, and of course its acceleration is inversely proportional. Since it's smaller, it's able to accelerate faster. Okay, now let's take a look at this. Hopefully you guys looked at this formula as well. We're going to come back to this formula. We're not going to talk about it a lot today, but we're going to come back to this one. So net force is equal to mass. And then what is that MA? What do you think this MA means? What do you think that MA means? So just so you know, it means net force is equal to mass times acceleration. Whenever you see a formula like this, and I know you guys don't have a lot of experience with this, but whenever you see two letters like this, that is assumed that it is multiplication. So it would be net force is equal to mass times acceleration. Okay, so let's keep it moving. All right, last thing we're going to talk about, and then we got a tiny video for you, okay, is we're going to talk about mass. Now, we talked about mass before, but we talked about it in much more simpler terms, how much stuff something is made of. We want to give that stuff an actual name. So mass is a measure of how much matter is present in a substance. And when we talk about matter, yes, we're talking about all the states of matter. So solid, liquid, gas, and yes, plasma. So all of those different states of matter. And it's a measure of how much matter is present in that given substance, regardless of what state of matter it actually is in. So when we put the things on the scale and we get that number in grams or milligrams, we're measuring how much matter is in that substance. All right, y'all, let's move to the next thing. So pause this if you need it. Again, pause it for the notes, but I'm gonna keep moving forward. All right, so let's take a look at our friends from the International Space Station. Come on.
Hello everyone, I'm astronaut Randy Bresnik, living and working aboard the International Space Station. Now, on the space station, we live in a microgravity environment.
Microgravity.
The laws of physics will hold up? Come on, let's go find out.
By the way, check out his feet. That's something a lot of people are asking.
The acceleration of an object depends on the net force acting on the object and the mass of the object, or F equals ma.
Jolly good show.
Jolly good show.
Here we see that once the force of the thrust is greater than the weight of the vehicle, the rocket begins to accelerate.
Alright, we're going to start with something small. Something you might have at home. A little stick of chapstick. We'll go ahead and use our force being our bungee cord here.
Yeah.
Put it on our bungee, and we'll pull it back.
Ooh.
And you can see how fast it accelerates because there's very
Large acceleration. Saw that.
Next, we'll try a little spaceship. A little more massive, and you can feel that because as you move it, you can feel that the kind of the force, the extra force you have to push with your hand. So we'll put our spaceship on our launcher here. Same spot.
Much slower.
Notice it's flying a lot slower than that chapstick did. What we've seen is the same amount of force on a smaller, less massive object means acceleration's faster. Well, this is the biggest and most massive thing we have, so let's see how the acceleration is affected. Pull back the same amount on the force, and here we go.
It's going.
And there you have it. Newton's second law of motion in action.
Thanks, fam.
Thanks everybody for exploring a little physics with me today. Now I'm going to send it back to Earth so you can start your experiments. See you again real soon.
All right, thank you. Now, as you guys saw there, right, that the smaller chapstick had less mass, so when the same force was applied, it was able to travel much faster. And then as it became more and more massive, as you saw, mass went up, acceleration went down. So that is everything for today. We do have this assignment in here. You will have time on Monday to get this complete. So just realize that you will have time on Monday to get this complete. But if you want to go ahead and read it and get it done, the PDF is located right inside here. It'll just populate after like about 10, 15 seconds. You just have to give it a little bit of time to load. All right, and then I do have it also in here in Spanish if you need that. That is it for today. Adios, my friends. Peace.